Today's lecture is on rotation in rigid bodies, and it's sort of starts us down 3 lectures of the final topic of the course. But before I get into that, I want to clean up one last piece from the topic of rotating reference frames that we spent the last 2 lectures on. And it's mostly just to sort of round out the maths so that you can see a complete picture for this thing, having had a little bit of time to think about it with the other 2 lectures. So where I want to start on this is, in mechanics, what we do quite often is convert from Cartesian coordinate systems to polar coordinate systems and back again, okay? And so we can have some force, F, and as you know, we can write that in terms of x and y components, fx I hat plus fy j hat. Or we can write it in terms of polar coordinates, right? So we would have some fr r hat plus f phi phi hat, where r hat is our radial direction and phi hat is our tangential direction in this coordinate system. All right, we can do a similar thing for v. So we have some velocity, and of course it's just going to be the time derivative of position. And this would break into 2 components, v of r hat plus v of phi phi hat, and of course we know what Vr and v phi are. V of r is just r dot r hat, so it's just a change in radial direction, so it would be a radial velocity, and v phi here is basically r omega that you would know from first year, and we can write that basically as r phi dot phi hat, okay? Alright, so we can go pretty much directly from here to acceleration, right? So acceleration is r double dot, and that's d on dt of r dot, of course, which is just our line above. And so what we would be dealing with here is d on dt of r dot r hat plus r phi dot phi hat, okay? And before I take that derivative, I want to take one step and look at 2 geometric relationships for derivatives, okay? And I'll write them down first. First one is dr hat on dt is equal to phi dot phi hat, and the second one is d phi hat on dt is equal to minus phi dot r hat, okay? And at first, some of you will say, well, where did he pull these from? Some of you will go, oh yeah, I've seen these in my maths courses already. Just so we're clear on the same page, if you imagine changing your r hat vector, right? So it's a unit vector, so we can only change its direction. And so you can imagine in here what we do is we go from one particular r hat at time 1 to a different particular r hat at time 2. We've now got a change in a direction of that vector. We can treat that to basically be a vector sum. And so here's r hat t1, here's r hat t2. There would be some change in here, okay, delta r hat, which would be the difference between the 2. And of course, that thing is going to be running in a radial direction here, particularly if that's a small change, right? If you imagine this is now infinitesimal, these 2 vectors are almost parallel to each other. There's a very small change in angle in between here, delta phi, and that direction is perpendicular, okay? And so we would work this thing out. It's basically going to be phi dot, okay? Because this would be now going from d r hat on dt to delta phi on delta t, which is d phi on dt, which is phi dot. And then the direction would be perpendicular to your original radial vector, so it would be phi hat, okay? And so that's how we get this little expression just here, all right? It's just a simple little piece of geometry. And likewise, you could imagine changing your phi hat vector, right? So if you change it from time 1 to time 2, now you've got some change in this tangential component. Again, you can make a diagram that looks like this. This would now be your change in phi hat. And of course, as you go back to being infinitesimal there, those 2 vectors are almost, or essentially almost parallel to each other, and then that vector on the end is basically perpendicular, right? So this is now pointing in your minus r hat direction, and this is now going to be phi d phi on dt, or delta phi on delta t, which is d phi on dt in the infinitesimal limit, which is phi dot, okay? And so what you get in here is your phi dot, and then the direction is minus r hat, which is where you get the minus sign and the r hat from, okay? So these are just little geometrical relationships that get us to little derivatives that we need in here. So if we pop back up to this line here, what we need to do here is deal with this as a product rule differentiation, right? So our acceleration here is going to be, we take the derivative of the first term, so r double dot r hat, plus the derivative of the second term, so r dot dr hat on dt. And then for the term on the end, there's 3 terms in the product, so we got 3 terms that pop out of this, okay? So we're going to have r dot phi hat, so that's taking the derivative of the first one, plus r phi double dot phi hat, plus r phi dot d phi hat on dt. Okay, so derivative of the first, derivative of the second, derivative of the third, all up we get 5 terms. All right, so now what we can do in here is substitute those 2 relationships we just got. So we've got r double dot r hat plus r dot phi hat plus r dot phi hat. That term just carries down. The next term just carries down as well, phi double dot phi hat. And then this term on the end is going to be r phi dot times minus phi dot r hat on the end, okay? And so that's just using these 2 relationships that we just pulled out from basic geometry of the system, okay? We can now go through and cluster the terms. And you'll notice 2 of these terms in here are common, right? This one and this one are the same, so they will just add together. So what we can do is cluster the r hat terms first. And so the r hat terms will be this one here and this one on the end. So what we'll get here is r double dot minus r phi dot squared r hat plus all the green terms will add up to give us r phi double dot plus 2r dot phi dot phi hat. Okay, and you'll remember way back up above we basically broke our force up into components fr and phi, and we can do that again down here. So what we can do is pull this line down here and go fr is going to be, we have to add a term for the mass to convert from acceleration, r double dot minus r phi dot squared, and our f of phi is going to be m r phi double dot plus 2r dot phi hash, phi hat, sorry. And you'll notice that we now have 4 terms in here as components, and we can break these out really quickly, right? This one here is just a radial acceleration. This one here is just a angular acceleration, and we know both of those terms, right? So one is just r double dot, the other one is a phi double dot. Then this term here is either, you can see it as centripetal or you can see it as centrifugal force. And this guy here is actually a Coriolis force. And I'll let you convince yourself of that one. We'll do that in a couple of lines anyway. You'll see that these 2 things are the same, but if you want to stop at this point and just check that that really is a Coriolis force, go for it. And so you'll notice in here, basically, we got the same thing that we got in the last lecture by using this relationship for how the time derivative of a vector in a rotating coordinate system changes. Here all we've done is just a transformation from polar coordinates to Cartesian coordinates, and the same thing pops out. Okay, so a little bit of what I'm showing here is basically just the way that physics is consistent, in the sense that sometimes you can take multiple approaches to the same result, and it's useful to know both that you can do that, you know, that physics is consistent irrespective of sometimes which way you come at the result, and also sometimes it's useful to know that there's multiple ways to come at results. Okay, now there's one more step we can take in here, and that is basically to consider a non-inertial frame S dash. For some reason my brain likes to reject the word inertial. I always, if I'm typing it, I spell it incorrectly. If I'm writing, I have to think about it halfway to make sure I write it correctly. It's kind of weird. Okay, so we're going to introduce a non-inertial reference frame here, and we're going to be very specific about it. We're going to call it a co-rotating frame. And some of why I'm doing this maths here also is a clandestine way of setting up a co-rotating frame, both so we can use it later and so you can use it in other courses as well. Okay, so when we have a co-rotating frame, what we're doing is we're taking our inertial frame and our rotating frame, and we're specifying that our rotating frame does two things. One, it rotates at the same angular frequency as an object of interest. And we did this implicitly in the last lecture when we basically had our rotating reference frame rotating at the same angular velocity as the Earth all the way through that problem. So we've already had a co-rotating frame. The other thing we do is we make sure those two systems have the same origin, okay? And that enables us to basically specify position vectors in a sensibly common way, okay? So the important thing about this co-rotating frame that we can write down straight up is that its rotational velocity omega, and that's big omega, is equal to phi dash, right? We set it to be the same as the rotation of the object, okay? All right, so we have an object, or we can call it a particle, and it has coordinates r dash and phi dash in that frame. And the reason why we set our origins to be the same is that what we want to do is then be able to say that the magnitude of r is equal to the magnitude of r dash. Note that I'm dealing specifically with magnitudes and not with the vector quantity here, okay? So what I'm saying is, you know, if I consider position in those two reference frames, the direction associated with it might change, obviously, because one's rotating relative to the other, but the distance from that origin to whatever I'm interested in will stay the same because it's rotating in a circle, okay? So that's the only requirement I've put in here at the moment. The other thing that we'll do, because it's co-rotating, we know that it's not accelerating, right? So we know that phi dot for our co-rotating reference frame is going to be 0, okay? So in other words, if we think about our rotating reference frame, that particle is kind of fixed in it because it's moving with us, okay? All right, so the thing we learned in the last lecture is that if we want to deal in a rotating reference frame, what we have to do is add two fictitious forces to our overall force in order to cope with the fact that the reference frame is rotating, okay? And so the first part of the maths that I did back before was just a normal inertial reference frame. Now I'm doing it for the co-rotating frame, okay? So what we would have here now is F, and we add our two fictitious forces. So we would have our centrifugal force and our Coriolis force. And these will give you mr double dot dash, okay? Which is just the acceleration of the object in that co-rotating frame. Okay, so we can pull some results we know from our last lecture, which basically is that in this particular case, the centrifugal force is going to be purely radial, and we know what the magnitude of it is. It's mr omega squared, okay? And we could also call this mr dash omega squared because we know this relationship in the magnitudes, okay? And of course we're talking about a magnitude over here at the moment, and the direction is that we know that it's radial, okay? Our Coriolis force is going to be 2mv cross omega, and you know this from the earlier lectures, but we know that v must be purely radial in the co-rotating frame here. So the Coriolis force is going to be in the phi dash direction with a magnitude minus 2mr dot omega, okay? You might want to stop here and just think your way through this for a second. What you're going to have in this co-rotating frame is that your particle is moving in a circle, right? And the reason why it's moving in a circle is we specified just up above that our distance out to that particle is fixed in both of the frames, and so it must be moving, you know, tangential, and that means that the Coriolis force is going to have a particular direction we can work out. We can work out what the magnitude is from the cross product, right? So we can knock out that sign, okay? All right, so what we can do here now is basically just pull this all together. So what we've got is F plus F CF plus F Coriolis is M R double dot dash, and of course this thing is now going to be f of r hat plus f of phi hat, and those just come from this force term, plus m r omega squared r hat minus 2 mr dot omega phi hat dash, okay? And we know in here two things. We know that omega is equal to phi dash straight up, so we can collapse those two terms together. And we know that phi dot dash is going to be equal to phi dot, okay? In other words, because we got a co-rotating reference frame, the speed that we would see the particle rotating from our inertial frame will be the same as the velocity of rotation of that co-rotating frame, okay? And so if we do this, what we've got in here is mr double dot dash is equal to fr plus, we've got a radial term here that we can pull in, so this is going to be mr omega dot squared, and this will be in the radial direction, plus f phi minus 2 mr dot phi dot phi hat. And so we can pull this down one more step here and basically write that f of r plus m r phi dot squared is equal to m r double dot dash in the radial direction, so there's our radial component, and then f of phi minus 2 mr dot phi dot is equal to m r double dot in the phi direction just here, okay? And what I'm basically saying here on this right hand side is that my change in position can be made up of some radial component and some phi component, okay? All right, so if we now pull these two things together, And I've put them on the slide basically to save myself from having to scroll up and down on my notes. But basically what we're taking is what we had up here and comparing it to what we had down here, okay? And so this is now for our frame S, and this would be for our frame, this is for our frame S dash, and this is for our frame S up above, okay? So for our inertial frame, we worked out something that looks a little bit like this. And this was just doing a transition from Cartesian coordinates to polar coordinates. Then if we think about our co-rotating frame, what we get is something that looks like this from the logic we just did, okay? And what you'll notice is that they look exactly the same, except now we've got the centrifugal term appearing on the two different sides in the radial component, and we've got the Coriolis term turning up on the two different sides in the tangential component, okay? And I think this is significant for two reasons. One is that it doesn't matter which frame you're in, these forces will kind of turn up neatly by themselves, okay, as long as you do the maths correctly. And they will turn up on different sides depending on which you deal with, okay? So if you think about your inertial frame, what's nice about it is that the forces are simpler, but the accelerations are more complicated, okay? So taking that approach of working with inertial frames, you actually build these extra terms into your accelerations rather than building them directly into the forces. And then for your co-rotating frames here, they now appear on the force side, and so the force ends up being more complicated. You have to introduce fictitious forces, you know, centrifugal force, Coriolis force, and so forth. But the accelerations are simpler in that process because we make the frame rotate with that object, okay? The other important thing here is that both are equally valid, okay? And what we can do is we can choose which one of the two we want to work with based on convenience for the maths, okay? So sometimes it's easier to deal with these terms as these sort of, you know, added on forces in a co-rotating frame. Sometimes it's easier to deal in the inertial frame and deal with them as accelerations. Either approach should give you the same answer as long as you do the maths carefully enough, okay? So that's pretty much where I wanted to finish off with rotating frames, just tying those two ideas together into one package. And to show that we can get them without relying on that vector relationship that we had in the last lecture. Although in the end, you know, that's kind of a consistent part of the maths with the maths we're doing here as well. Okay, so that brings us to rotation in rigid bodies now that we understand rotational coordinate systems. And rotation in rigid bodies matters in mechanics courses because it's a more complicated system to deal with. It's why we sort of spend a couple of lectures on dealing with it. And usually in mechanics, we start out with particles to keep things nice and simple, but what we want to deal with is more complicated objects, right? Like a basketball or a stick or, you know, some funny shaped object that's moving along. And when you think about linear motion with sort of a complicated object that's made up of, you know, a whole pile of parts as a rigid body, size and shape don't matter very much, assuming you can, you know, get rid of atmosphere and stuff like that, right? And so what ultimately really matters is just the mass and the parameters attached to it, you know, its position, its velocity, its acceleration, that sort of thing. And so you can predict the motion, you know, sort of for linear motion as well for a basketball as you can for an electron or a rocket, using exactly the same equations, right? When it comes to rotation very dependent on size and shape, and so we need to account for that. And the reason for it is, and a lot of books don't really go into this, the reason why in the end there's a difference between the two is that in linear motion the momentum is just made up of the mass times the velocity, right? The mass is a simple scalar object, the velocity is just a vector, and assuming you attach everything to the center of mass, the linear motion is kind of simple, okay? When you deal with angular momentum and rotation, the momentum for a rotational problem doesn't just have the mass and a velocity in it, it also has a radius. And of course, when you have a rigid body, every single point in that rigid body has a different radius. So what you need to do is work your way around all of those radii to deal with it. And if you change the shape of the body, you actually change those radial components that contribute to it. And that's what makes it complicated, right? And you'll notice there's no radius term or nothing relating to the positions of things in the object in the linear momentum, okay? And so the r term in here is not just r, it's r squared, and that makes it even more complicated, right? It's actually a pretty powerful contributor. If you add mass away from, you know, the center of your mass or center of motion, you have a very big multiplying effect of that thing that acts in that problem, okay? And so that's why we can do linear motion of rigid bodies really, really easily in first year, but rotation of rigid bodies is a problem that needs some, you know, serious techniques. Okay, so in this half of the lecture, I basically want to get through three little aspects of this to set ourselves up. One is center of mass, the other one is total momentum, and the last one is angular momentum. And then in the second half, which will be pretty quick to get through, we're going to deal with kinetic energy and what was the other one? Setting up moments of inertia for a really simple system, okay? And we'll come back in the next lecture and deal with a lot more complicated versions of inertia tensor and that sort of thing for rigid bodies, okay? All right, center of mass we can define pretty quickly and easily. So again, for all of the problems in here, it's probably worth thinking about you know, an object like a ball, okay? And for the moment, we can keep it kind of simple and assume it's a sphere. And as we get through the next two lectures, we'll actually move away from spheres to more complicated shapes because they're the ones that, in terms of rotational motion, can actually be quite interesting. All right. So if I take this ball, I can break it up into component parts. You can imagine that I just chop it into atoms. So there'd be, you know, 10 to the 23 particles in here. Each of them has a mass alpha, which would be atomic mass. Each of them has a position alpha relative to some origin O, and I can put that origin O anywhere I like. I can put it here, I can put it up there. Both places are probably kind of dumb. I can put it at the center of the object. That's probably the smart place to put it. I can put it some other place in the object if I want to, okay? What we can do relative to that coordinate system, and I can set it up outside if I want, is define a thing called the center of mass. And it's basically sort of the average mass position for that object, okay? And so what we do here is we take, it's essentially a weighted average, right? What we do is we take the mass of each component particle, multiply it by its position, add all of those up. So the ones that are further away will count for a little bit more, the ones that are closer will count for a bit less. You'll notice that we've got no squares in here, so something on one side of the object will cancel out something on the other side of the object. We add all of that up, we divide it by the total mass of the object, and what it really tells us is where the center of that mass is. And what that really means is, what is the position where the balance of mass on one side is equal to the balance of mass on the other side, looking at all sides of this object, okay? If you're doing it discrete, it looks like a sum, just like this. And as you all know, if I take the individual particles in there and I take the infinitesimal limit for this, that sum becomes an integral. And so what we really have here is just 1 over the total mass times the integral of all the positions and their little mass component dm, okay? One thing to be aware of is that generally the center of mass for simple objects is right inside the object. And so for, you know, the simplest case I can imagine here, which is like a spherical ball, it's going to be the center of the ball, assuming that I've got mass distributed homogeneously through this thing. What I could do is cut this ball in half, make half of it made out of foam, half of it made out of lead. Then this side's going to be heavier, so that center of mass will move towards that side that's got the lead in it. Okay, so let's make that side the lead. It's going to move to this side. Okay, joys of having to work in a mirrored camera situation. And then sometimes, if you've got mass symmetry and geometry symmetry, it's easy, it's in the middle. If you break that symmetry, then that moves. Sometimes you can actually get the center of mass to be outside the object entirely, okay? And so there's this nice little demonstration here where you can make an object where the center of mass is actually right at the tip of this little bird's beak here, and you can see the nice thing about center of mass, if you position yourself, position the center of mass on a balance point, it will balance quite nicely. And you can see here that that's actually at the edge of the object because of the way the mass is distributed in this object, okay? And so the way this thing is designed is kind of heavy up the front here and light at the back, so that that balance, a little bit like in this ball, making it half with lead and half with foam, will pull that center of mass towards one edge because of the contributions of this mass term in all of those parts, okay? And so very useful thing to have, center of mass, because it determines, you know, if you try to balance that object, where that's going to balance. And ultimately, in a lot of cases, what it's going to try and rotate about. Okay, so that's center of mass. We can define a total momentum for a body, and that's kind of simple as well. And the nice thing we can do for a lot of these objects, and you may have seen this in first year, is we can start to talk about everything relative to the center of mass, okay? So the total momentum in here is basically the sum of the momenta of all the little particles in here. So you can imagine that, you know, if I throw this ball, basically what I'm doing is throwing all alpha of the particles in such a way that they all move together. And then that will be basically given by mass times velocity, which is this term just here. And we can basically treat a rigid body, as far as its total momentum is concerned, as just what they call a center of mass motion, right? So we basically tie the full mass of the object to its center of mass and just treat the motion of the center of mass, assuming that the entire rigid body will follow its center of mass, okay? And of course, then we can take the external force as just the time derivative of our momentum, and so we get a really simple expression like this: F external is equal to big M R double dot. Okay? And this kind of highlights the point why we don't really care much about shape when we deal with linear motion. Okay, you'll notice in here that the shape doesn't necessarily enormously come into it. All we need to know is the total mass and what's happening to the center of mass for that object. And then we can deal with total angular momentum, and it's a little bit more complicated as a situation, okay? And the best way to think about this is to make it more general. So we can go from just a simple spherical object rotating about its center to something that's, you know, not necessarily spherical. You can see I'm going to have some fun invisibility games with my football. Not necessarily symmetric even. And we can work around some origin some distance away and basically work our way out to all the points. And the interesting thing to note is that there's actually, at the moment, we can see two types of motion that we have to account for angular momentum of, right? Whereas with linear motion, it's just the center of mass moves and the whole thing, there's just one term. Here we can have a rotation that looks like this, right? The object's rotating about itself. The other thing that we can have is that the object is rotating about a point that's outside the body, okay? And we have to account for both of those types of possible motion when we deal with our analysis here, okay? So the way we're going to set this up, we're going to have a body, we're going to have an origin O that's outside that object for now. We can position it anywhere we like. And what we're going to do is define some vector, big R, that is basically the position of our center of mass. So we can track the center of mass of this object in space. And then we're going to have, for each of the little masses that make up this body, M alpha, we're going to have a position for that. So we're going to refer that back to our original origin. And then we can define a little vector in here, R dash. And now R dash is basically the difference between the position of the center of mass and the position of that object. In other words, what it is the position of that mass relative to the center of mass, okay? All right, now we start this thing with just a nice little vector sum in here. So we have R alpha is equal to R plus R alpha dash, okay? So all we've basically said in here is that this vector plus this vector is equal to this vector, okay? And we know that angular momentum of a little individual particle here is going to be given by the position alpha times the momentum alpha, okay? And you'll remember this definition basically working from first year. The other way to see it would be mr cross v. And so sure enough, we can write it as exactly that. So this is going to be r of alpha cross m alpha r dot alpha, okay? So what we're really looking at here is just this little position here. We're going to work out the angular momentum by looking at the motion of this little piece of mass at some distance away from that origin, okay? Now that is just the angular momentum attached to one little component, and the total angular momentum, L, is going to be the sum over alpha of all those little components, alpha, in here, right? So what it's going to be is essentially sum over alpha, r alpha cross m alpha r alpha dot, okay? Where this r alpha dot here is actually a vector, just to be really clear, right? Because we've got a vector cross product and mass is a scalar, so the vector has to be attached to something. It's essentially there's a direction attached to the change in the position of the that little piece of mass, okay? Now, one thing we can use in here is our term for r alpha just up above. So what we can do is write this as sum over alpha of big R plus R alpha dash times M alpha, and so that times is actually a vector cross product, just to be clear, R dot plus R alpha dot dash, okay? And again, one of these things, it's kind of gets a bit ugly if I was to write like a R vector dot or a r dot vector, so you kind of need to keep a track of what's vector and what's not in here, okay? Particularly when you do it in handwriting, okay? All right, so this thing here now we can break up into a bunch of terms, right? Taking the individual components out. So this will now be sum, and I'm going to drop the alphas off the sums because it's pretty clear what's going on here. So this is going to be R cross M alpha R dot plus sum R cross M alpha R alpha dot dash plus sum R alpha dash cross M alpha R dot plus sum R alpha dash cross M alpha R alpha dot dash. Okay, so all I've really done is said that the sum of a product of two sums is going to be the sum of four sums. Okay, so I've got one term attached to this and this. I've got one term attached to this and this. I've got one term attached to this guy and this guy, and I've got one term attached to this guy and this guy, right? In here. And it's perfectly okay to do that decomposition as long as I respect the fact that cross product is commutative, so I don't swap the order, okay? If I swap the order, I've got to put a minus sign in, otherwise everything's hunky-dory. Okay, now the mass is a scalar in here, and so I can clean this term up a little bit here, and I'll just move it across so I can fit everything in. This is going to now be R cross. The sum in this first term here can apply directly to the mass, and that's just going to give me the mass of the whole object, M, R dot, okay? Plus this second term, I can pull big R out of the sum because the sum has no influence on it, so that's going to be big R cross sum over M alpha R alpha dash. Plus, in the third term here, I can pull this big R term out as well. So this is now going to be sum over alpha. The m alpha can go any side I want because it's a scalar. R alpha dot here cross R dot. And I still don't have enough room on my line, so I'm going to have to pull this fourth term down onto the next line, unfortunately. Sum over R alpha dash cross M alpha R alpha dot. Okay, so the last term I'm just going to leave alone. Okay, so I can number these terms, which is kind of why I wanted to get them all on one line. So this one's 1, this one's 2, this term here is 3, and this one here is 4 for a moment, okay? Just keeping track of the components. Okay, so we need to think about what these things are for a second. This term here in 3, sum over alpha m alpha r alpha dot, is basically going to be the center of mass relative to the center of mass, right? Which, if you think about it like that, it's got to be 0, right? How can you have a center of mass relative to a center of mass? It's kind of impossible to have such a thing. So basically in here, wrong color, what we have is sum of m alpha r alpha dash is equal to 0, and that also means that the sum over m alpha r alpha dot dash is equal to 0 as well, right? Because if I take the derivative of something that's 0, then I must get 0, okay? And so what happens here is that this term here is 0, and this term here is 0 as well, because I've essentially got terms that are center of mass relative to center of mass, which is the same thing, so they collapse to 0, okay? You'll notice that this term out the front stays alive, and this term on the end here stays alive as well, and it stays alive as well because of the cross product that's hanging around inside it, okay? You'll notice that I can't really pull the sum from this position here into that position there, so that I can cancel out the center of mass like I can in 2 and 3. It's got to hang. And so what I can do in here then, as a final step in here, is say that L is going to be R cross M R dot plus sum over alpha R alpha dash cross M alpha R alpha dot dash in here. And then I can use the expression I had on my last slide to deal with this piece here. So this is going to be R cross P plus sum over alpha R alpha dash cross M alpha R dot alpha dash, okay? And if I think about this thing, I get this expression just down here, and I can actually break this up into 2 components, right? The first component, this R cross P, is basically what we could call an orbital angular momentum. So if we think about this for a second, what we have is this object, say, spinning on its own axis and rotating around some origin, right? And so this component that we have, R cross P, is basically just this orbital motion, okay? It's essentially the motion of the center of mass of the object around the center of our coordinate system. And then the second component we have is basically a rotation of the object around the center of mass, right? And you can see in here basically what we're doing is taking the momentum of a component of that mass at its distance from the center of mass and working out that angular momentum. And so that's basically a spin component. That's the object spinning on its own axis. And so essentially what we've done here is take our angular momentum, break it up into 2 components. One is the center of mass motion, and the other one is the motion of the body about its own center of mass. Really common thing to do in rotational motion. We'll come back to it again and again as we go along. And probably a good place to stop for a break before we get on to the rest of the lecture.